Okay. So welcome everybody to a new quantum space seminar. Today we have Esperanza Cuenca Gomez. She's an engineer, but and also is a developer in relations manager for quantum computing at NVIDIA. She has background in consumer finance, banking, strategic consulting, and she has applied science and engineering as a way to build new technologies, solve problems, and contribute to society. Today, she's going to talk about these issues, and specifically, the title of talk will be Programming Heterogeneous Quantum Classical Supercomputing Architecture. The whole seminar is around 1 hour. 45 minutes plus 15 minutes of questions. If anybody has questions, please raise your hand or just put it in the chat, and we will communicate. Thanks. Esperanza, please.
Well, thanks everyone for having me. I'm thrilled to be joining all of you today. And during this hour that we are going to spend together, I'm going to talk about how to program heterogeneous quantum and classical supercomputing architectures. So the outline of my talk, I'll start speaking about NVIDIA, HPC, and quantum computing, and why GPUs and QPUs. I will be also explaining what is CUDA-Q and share some works using this platform. I will be delivering as well an overview of the CUDA-Q language. And I will also be addressing QQuantum, which is one of the backends for CUDA-Q. But let's take one step at a time, and let's get started. So NVIDIA, HPC, and quantum computing, why GPU and QPU? Well, we believe that supercomputers are at the foundation of quantum research and development. And in this talk, I'm going to go from a general overview, a high-level vision, and then I will be delving into more details. So at this conceptual level, we can use supercomputers in 3 ways to accelerate quantum computing. One way is simulation. So quantum computers currently face some challenges. So simulation is an essential tool to help to overcome those challenges. Today, powerful simulators enable algorithm and application research and development, new approaches for that. And in the future, I think that we'll have digital twins of quantum computers for design and architecture optimization. When we think about HPC quantum integration, or more generally, classical quantum integration, we think that useful quantum computing will be hybrid. So today, one goal is to enable domain scientists to start developing for QPUs and enable quantum researchers to use accelerated computing, and not only quantum researchers, quantum developers, people working in quantum in general. And in the future, quantum computers will integrate tightly with supercomputers as accelerators and will be co-programmed. And the third pillar that I wanted to talk about is AI for quantum. So error correction, calibration, control, compilation are challenging computationally, and we often need real-time compute. accelerated computing and AI can solve these problems. So today, a focus would be to enable AI research for all of the above. And in the future, we'll have hybrid and AI supercomputers very tightly integrated with very low latency links. So how do we power all of this, and how we power the global quantum computing community, addressing each of the pillars that I have discussed before? Well, CUDA-Q is a platform for that. I will be explaining this in more detail, but CUDA-Q has a number of libraries. It's a programming model. It has tools, and it also leverages on infrastructure. And as I was explaining when I was showing the outline of my talk, QUantum is the backend that is integrated into CUDA-Q for quantum simulation or emulation, if you wish. And DGX Quantum is a reference architecture for very tight integration of quantum and classical devices. So here, I'd like to elaborate a little bit more on the need for this integration. This is basically a reinforcing of what I have been saying before. But I also like to focus in some problems and workloads. For example, quantum chemistry, material simulation, AI. And I also wanted to stress that we expect that CPUs and GPUs will be able to enhance the performance of QPUs, for example, through classical preprocessing. A case of this is circuit optimization and post-processing, for example, error correction. Optimal control and QPU calibration and hybrid workflows. Okay, so what are the requirements for programming the hybrid quantum classical node? Well, we need performance, we need familiar programming models, and we need integration with existing compilers and runtimes. And C++ is the least common denominator for programming languages for a number of reasons. Like we can see some of those here. And then CUDA-like programming models have a specific features or characteristic such as cleanly separate device and host code, direct versus library-based language station, and a split compilation. So in summary, these are the requirements. And it's also important to leverage today's compiler technologies. So in developing CUDA-Q, we do not aim to reinvent the wheel, but to leverage frameworks and tools that are already there. So introducing CUDA-Q. CUDA-Q is the platform for unified quantum and classical accelerated computing. And it's a programming model extending C++ and Python with quantum kernels. It's an open programming model and an open source compiler. You can see here the GitHub tweet is QPU agnostic, and we are happy to partner with QPU builders. It's interoperable with the modern scientific computing ecosystem, and it's also retargetable, allowing a seamless transition from simulation to physical QPU, and I will be showing an example later on. In terms of the syntaxes, those of you that program frequently can see here, let's say from a first sight, something that at least sounds familiar. And this is the CUDA-Q stack. So how is this thing built? Well, as front ends, we can have C++ or we can have Python. And I will be showing later on some specific examples in Python as well. MLIR as the CUDA-Q intermediate representation, and then using QIR as the quantum intermediate representation. And then here we can see different backends, in this case for simulation, and physical QPUs for simulation. There are also more QPUs. I should have updated this slide because Orca Computing is also an online backend that we currently have. And this is the compiler platform. So I'm going to show now 2 examples of CUDA-Q in action that I believe are representative of what we can do with CUDA-Q. So this is a collaboration done with Hewlett-Packard Labs, and the aim is to study the dynamical quantum phase transitions. And this requires the computation of overlap of initial state with time-evolved state. And this was used leveraging NVIDIA multi-node, multi-GPU simulation backend, which is also, available for download it. It's almost open source, so and no fees attached, so everyone can use it. And using a distributed state vector simulator. You can see here the code snippet and also a snippet of the circuit to use. In this case, what I wanted to highlight here is this graph where we see the simulation time, the number of qubits, and in different colors, we see whether we use GPUs, one NVIDIA A100, 16 A100s, or 5012 A100s, which is this color. And what we see here is as we scale the number of qubits, we have speed ups in all of them. And there are number of qubits that CPUs are enabled to reach. So this is an example of CUDA-Q in action. This is another work. You have the reference here. I can share all of these with you later on. This was the development of a novel generative per-train transfer-based, or GPT, if you wish, methods for computing the ground state of molecules of interest. And it's the first demonstration of a GPT-generated quantum circuit in the literature. And this is an example of using AI to accelerate quantum computing. And it was executed using CUDA-Q on A100 GPUs on Perlmutter, which is a supercomputing center. And this opens the door for other generative quantum algorithms that can be used for drug discovery material science and other challenges, for example, environmental challenges. And so a summary of the results, you can see here the exact curve, and you see here how this algorithm performs, which is almost exact. And I'm happy to share with you the paper whose leading author was Professor Alana Spurgusic. So I believe it's a representative example of what you can do. I'll be starting now on sharing some further examples, at least part of them, because I have brought quite a lot of examples to share with you. So let's get started. I'm going to start with CUDA-Q, which is the platform that I'm discussing. Here you can see, well, the links to download, and you can see also here kind of a diagram which illustrates where CUDA-Q sits. And this is an example of how CUDA-Q performs, or QUantum performs, against a Pythonic framework. In the case of the async model trotterization circuit times. So this was done on A100, again, A100 GPUs, and using a state vector simulator versus a Pythonic framework. This is the example that I was talking about before. So in this case, one of the backends that one can use in CUDA-Q is Quantinuum. So in this expression and in this figure, we use as backend QUantum, which is our simulator for VQE, right? So if we change the target, and changing the target is changing this flag to this one, to Quantinuum, well, the results are consistent, and it's something easy to do. And this illustrates the point that I was making before about the seamless transition. As I was saying before, QUantum is a backend to CUDA-Q. It's integrated. You can also use it with another simulation frameworks. However, my recommendation would be to use it integrated in CUDA-Q, basically because this way, what's expected is to have the better performance. So here are, if you wish to use it with another framework, here they are. And here's another example of QUantum performance, which is significant in my opinion. And I also wanted to share an example of what you can do in this case with simulation applied to the max cut problem, depending on the accuracy, and using nodes on DGX. You see how you can scale. And this is, well, a final, let's say, slide about where you can find all the information about this. So up to this point is the first, let's say, part of my talk. Now I'm going to address some examples. I wanted to share the documentation. And so let me go here. So set all of these, which is in a sense a little bit theoretical. A question could be, all right, so where do I learn about NVIDIA Quantum? And how can I get started? So there are a number of places you can go. This is what I was showing before, which is let's say the portal or web page where you can see everything that we are doing in quantum. So, and here, for example, we have CUDA-Q. So, and here we have a developer technical blog with information about CUDA-Q, benefits, well, a number of things, and also features. And it's also interesting to see, to explore more resources that I'm happy to share as well. Technical blogs, news, explainer, lots of information here. And also, I think it's beneficial to see the documentation. So in this case, this is, I'm going to start here by the index. So as a quick start, the first step would be to install CUDA-Q locally and validate your installation. There are a number of ways to perform the installation, depending on which way you want to go. Some might be better than others. You can use a Docker image, and this is a path that a number of folks find useful. And so here, and you have instructions for performing the installation, either for Python or C++. And here you can see as well how to validate the installation. So this is a simple example to make sure that things are working. Okay, so let's go now to the basics. I want to pause for a minute in the concept of CUDA-Q kernel, because this is central. So CUDA kernels are basically functions that are executed on a QPU or a simulated QPU. And they generalize quantum circuits and provide an abstraction for quantum computing. So in a quantum kernel, you can combine quantum algorithms and classical functions to create quantum classical applications. And you can execute that on a heterogeneous system. So a question that I get is, so what's the difference between a quantum kernel and a quantum circuit? Well, every quantum circuit is a kernel, but not every quantum kernel is a circuit. So a quantum kernel can be built from another kernels, and also quantum kernels have more expressibility. Because you can parameterize, you can also add classical control flow statements and classical computations, as well as conditional statements and so on and so forth. And well, here you can see how to build your first CUDA-Q program, and I encourage you to run through these examples. And speaking about examples, we can see here a number of them. Some of them that for some of you might be kind of well known, such as the VQE and the QAOA. And we have here also applications another implementation of VQE max code with QAOA, hybrid quantum neural networks, noisy simulation, readout error mitigations. All of these are examples of codes that you can basically use. And I want to yeah, I will go back to some examples that I'm happy to walk you through, but I also wanted to speak a little bit about backends. So if we recall the graphic about how CUDA-Q is built, basically we have a front end for programming, then a number of compilation steps are performed, and we then execute that on backends. And we have different types of backends. We have simulation backends, quantum hardware, the NVIDIA Quantum Cloud, and also multiprocessor platforms. So let's start on simulation. So we have state vector simulations and tensor network simulators. These are, as I was saying before, QUantum. You also have a documentation specific for QUantum. It's integrated in CUDA-Q. So when you install CUDA-Q, you can use those those simulators that are accelerated by the different libraries. And you can see here how would you specify how you execute a program and how you specify a target. And what I think it's interesting in this case of state vector simulators, and I would go for tensor simulators later on, is that you can go for a single GPU simulator or a multi-node, multi-GPU simulator if you have access to that architecture. And then you can also use CPU only. And then for the tensor networks simulators, you can go for multi-node, multi-GPU, and also you can go for another way to do this is here you have a backend for matrix product state, and here is how you execute a program on this target and how you define that in the application code. So it's the same way as for the state vector. Okay. And here, you can see also the default simulator, which basically, if you don't specify a target, CUDA-Q will make a default choice. Going now for quantum hardware, here are the different backend QPUs that can be used as backends. To use these QPUs, you'll need to have some way to get access to this, as CUDA-Q doesn't handle that access. The access is handled by the QPU builder. And here we can see examples of how to set in credentials and how to submit jobs. It's pretty, let's say, standard process for the different QPUs. I want to spend now a minute speaking about NVIDIA Quantum Cloud. It is currently in early access, and the philosophy behind this is to use to facilitate the access to GPUs. And here you can, it's integrated in CUDA-Q, and here is how you set the target. You can see here NVIDIA Quantum Cloud set as target, and there are different things that you can do. You can select simulator backends. NVIDIA Quantum Cloud hosts all of CUDA-Q simulator backends, and you can also go for multi-GPUs executions and multi-QPUs asynchronous execution. However, the NVIDIA Quantum Cloud is currently in early access, so if you want to join, you're welcome to apply, and you'll need an account in the NVIDIA Developer Program to apply. So here it is, the Developer Program, and I can share this with you if you're interested. Okay, so when we were about to start, I have here some examples to show with a specific code. So one example that I wanted to walk through is the VQE. So this is an implementation of the VQE using CUDA-Q to see how this looks like. And also CUDA-Q has a built-in module. So let's see how this works. In a nutshell, given a parameterized quantum kernel, a spin system Hamiltonian, and one of CUDA-Q's optimizer, CUDA-Q VQE will find and return the optimal set of parameters that minimize the energy set of the system. So I'm going to make this a little bit bigger. Okay. So we begin by defining the spin Hamiltonian for the system that we are working with. And we do this by using the use of CUDA-Q spin operator. And this, what allows is the creation of Hamiltonians out of Pauli spin operator, sorry. And then we use the expression CUDA-Q kernel to define the variational quantum circuit that we'd like to use as an answer. And so we create a kernel that takes a list of floats of a function argument. So here basically we do the definition and we allocate 2 qubits and we apply an airway gate that is parameterized by the first value of our angles. And we see the expressions here. It's important to note that the kernel must not contain measurement instructions. And then we pick an optimizer from the suite of CUDA-Q optimizers. And in this case, we pick Cobila. We can also tune this optimizer. And finally, we pass all of this through the CUDA-Q VQE, and then it will run our optimization loop, and it will return a tuple of the minimized eigenvalue of our spin operator and the list of optimal variational parameters. And okay, so a more advanced variation of this example is using the CUDA-Q optimizer suite on its own to write custom variational algorithms routine. And well, we start pretty much the same way as we did before. And here is where we define the optimizer that we'd like to use. Here, we'll be using a gradient-based optimizer. So we will be leveraging the CUDA-Q gradient helper class to automatically compute the gradient vector for us. And this is optional. You can use your own custom gradient routine. But for the moment, we are going to go with this. And then we call CUDA-Q observe on the spin operator and the ansatz at the optimizer provider parameters. And this will allow us to easily extract the expectation value of the entire system in the set basis. And we define the call to CUDA-Q observe here as a lambda to allow it to be passed into the gradient strategy as a function. And if you were using a gradient-free optimizer, you would use this definition that you can see here. And here is how we code this. So CUDA-Q observe returns a CUDA-Q observe result that holds the counts, dictionary, and the expectation. And then we compute the gradient version using CUDA-Q gradient strategy compute and return the cost gradient function tab. And we make this repeatable. So yeah, and we finish by printing our results. So this is one example. It's an introductory one, a simple one, so to speak. I want to also dedicate a few minutes on the QAOA. Actually, for the QAOA, we have two examples. So this is a basic one or more compacted one. This is one with more, let's say, explanations into that. So the code is very similar, almost equal. So I will go for the short version, as I also want to allow some time for questions. So basically, what we are going to do here is to implement the QAOA to compute the max cut of our rectangular graph by leveraging CUDA-Q VQE. And if you want to see more information, you can take a look at this paper and also this link, which is in the section about tutorials. So the objective here is to build a kernel for QAOA with P layers, and each layer containing the alternating set of unitaries corresponding to the problem and the mixer Hamiltonian. And this is the graph that we will be tackling, which is trivial one, but the point here is to understand the basics. So we start by formulating the problem Hamiltonian, the problem parameters, and here's the CUDA-Q kernel. And then we create superposition and we loop over the layers and loop over the qubits, sorry. And here what we do is we specify the optimizer and its initial parameters and make it repeatable. And define the objective and return this basically. And then we optimize and print the optimized value and its parameter, and we sample the circuit using the optimized parameter. I'm getting kind of close to the time for questions. So I'd be happy to share all of this information with you. And also, I'd encourage you to take a look at all of this and reach out with any observations or comments or questions that you might have. I'm gonna stop sharing my screen, and I'd be happy to take questions and comments.
Thank you very much, Esperanza. Now it's the turn from the people. If there is any question.
Where's this?
I have a question about this collaboration that you put about the different quantum kernels, you call it. So all these different providers. Is it possible then to have access to all these possible quantum kernels with the NVIDIA software? There are some of them that didn't appear in this in the slides that you put there. And also, is the purpose of NVIDIA to cover all possible providers, or I don't know?
Yeah, let me address the question. So it's actually the QPUs can be part of a quantum kernel in the sense that you can call a QPU from a quantum kernel, but it's a slightly different concept, okay. I'd say. So what we have currently online integrated are the different QPU builders that I have shown. And what this means is that you can submit jobs directly from CUDA-Q if you wish to from the QPU builder that is online integrated. If it's not, well, some work would be needed to do that integration. But let's start with the one that are already integrated. So the point here is that we don't handle the access to the machine. So for example, if you want to access a machine, I don't know, by whichever QPU builder that is integrated, you will need to have some kind of agreement with them. So you have credentials, and depending on how they manage access, you'll need, I don't know, tokens or things like that sometimes they require. But we don't handle the access with them. Let's say we provide a way, so to speak, to do this, but you still need to figure out how to get into the machine, basically figure out and make sure that when you are sending jobs from CUDA-Q, you have the right credentials in place so their machine can accept those jobs.
Mm-hmm. More questions or comments in the audience? So if not, maybe Javier and Esperanza, maybe we can close it here.
Yes.
And we reconvene for how long is the next seminar? When is the next one?
Now we will wait until next academic year, September.
Okay. So till September we'll have the next seminar here in Quantum Spain. Okay. Thanks a lot, Esperanza.
Thank you very much.
Okay. Thanks everyone.
Thank you.
Bye.
Thank you.